All right, well, hello, everyone. Welcome. My name is Dan Craig. I'm a software engineer at Varda Space Industries, just up the freeway in El Segundo. We build satellites and reentry capsules that manufacture pharmaceuticals in orbit and return them for use here on Earth. I have a lot of fun at my job. I get to work with spacecraft every day. And as much fun as it would be to talk about spaceflight, and ask me later about a happy hour if you're interested in that. Today I'm going to talk about something a little more down to earth. Command line interfaces. We write a lot of Python programs at Varda, from small helper scripts to data review to mission planning to the servers and clients that run our ground segment. And every one of these applications is started from a command line invocation, as I suspect most of your programs are. What we're going to do here is kind of like build up some good patterns of how you can use argparse to make very effective and very testable applications. There are a lot of great third-party libraries out there, and we'll talk about some of those at the end. But for the kind of simple use cases, like kind of the 90% use case, I think argparse is great, and with a few good patterns, can be very maintainable and testable. OK, so we're starting at the beginning. Like, how do arguments even reach your application? In Python, command line arguments are available through sys.argv. So let's write a simple script here that will just print this object, and we can see what it is. We see it's a list. It contains the name of our script, plus however many things that we pass after that. So why does it work that way? And what's with the v in argv? OK, well, this one's maybe a little easier. Like most fundamentals of Python, it traces to the C API, which itself is directly built on the execve syscall that the operating system uses to execute a program. And every C program starts with a main function that returns an integer. It's like int main here. It takes an argc and an argv arguments. Argv is the argument vector in the form of an array of pointers to strings that are passed as the command line arguments. Argc is the argument counter, which is effectively the length of the argv vector. And of course, since in Python we're using a list, so we don't need, you don't need a separate variable containing that length. By convention, the first of these strings in the list is the file name associated with the program being executed. And the integer being returned by main is the program's exit status. And so remember that imaginary function signature that you can't see on the screen there, because we're going to come back to it later. Nope. OK. We'll talk a little about how does the text that you type into command line go? So how do we go from just a string of bytes that you type in to a list of strings? Well, that's the job of the shell program, like bash or Z shell or others. The shell translates the literal text that you type into the command line and determines what program to execute and what list of arguments it should pass to that program. And so that's how things like quoting and glob expansion work. Your program never sees the star that you type in. The shell translates that into a list of all the local files and then passes that list into your program. Nope. OK, let me push that. OK, so now an astute observer of the slide you couldn't see might have noticed that something that the argv that the Python script is printing here does not quite match the command line call. We see print args.py and we see Dan, but the program that we ran here was Python, not print args.py. We can see this more illustrative if we pass arguments directly to Python, like the -i argument here. We still get the same thing of just these two arguments. And so what's happening here is that Python is consuming these arguments before passing them on to our script, which makes sense because those are arguments for Python, not our script. And so remember that by convention of the list of arguments, that Python is following that convention in kind of a way that seems obvious that our script, by the time it gets to being run, is the program being executed. OK. The last thing to note here about the C API is the concept of exit statuses, sometimes also referred to as return codes. This is the integer returned by the main function of C programs. By convention, in POSIX operating systems, a program that exits 0 means that it exited successfully or that it returned true. Non-zero means failure or false. Python, by default, returns 0 when a program completes. So usually you don't ever have to think about the exit code of your program. If an unhandled exception is raised, it'll return non-zero. Yeah, OK. So let's write a simple Python script that will just compare two values for equality and return 0 if they are true, and return 1 if they are different. And we manage the exit status here by explicitly using sys.exit and passing that number that we want to exit here. And so now we can use this program in a bash expression, such like this conditional here that will print one string if the values are equal and another if they are not. But it's brittle. What if we pass only one output, or input? Then we're going to get a gross stack trace. What if we pass too many inputs? It'll quietly swallow them, and we'll never know. And just how are we supposed to use this thing? Same gross stack trace if we ask it for help. So we could, of course, roll our own handling of sys.argv, but that's exactly what argparse is for. So let's rewrite this comparison program with argparse. To do this, we create a parser where we can describe what the program does. We declare a couple of positional arguments, and then we call parse args, which will collect the command line arguments and return them as a namespace object. And then we can now use those arguments in the rest of our program. So now we have some error handling. If we return the wrong number of arguments or too few, it'll tell us in a nice way. We have some help text automatically. And this is already way better with just a couple lines of code. We can also refer in our program to the arguments by name instead of having to do by positional index there. Now, you might have noticed that sys.argv is nowhere to be seen here. So what happened to it? Well, argparse's parse args, by default, will look at the second through remaining elements of sys.argv. You can pass that in directly, but by default, it'll work that way. But remember that you can pass it in directly, because we are going to come back to that, too. All right, so this equality checking program is pretty cool, but let's make something a little more interesting. A program that checks if one of the values is greater than the other. So it seems easy enough, right? All we need to do is change our double equal to a greater than. But when we run it, we see that it gives us the wrong exit code. When we give it 2 is 2 greater than 1, it's returning 1, which is not right. And then we remember, oh yeah, right, we're dealing with strings here, not with integers. Because on the command line, all arguments are strings. Remember, argv is all just a list of strings. And so argparse will run with that unless told otherwise. Now, we could wrap our values in float at the time we compare them, but there is an easier solution, which may or may not come up here, which is to pass the type argument when we do add argument. So this is nice, because it'll give us some helpful error messages if we pass a thing that can't be cast into a float. But it doesn't have to be just a type, like int or float. You can pass any callable as the type argument, as long as it returns the thing in the format that you want. So you can do some neat things like passing dateparser.parse, so that users can pass a timestamp in a very human-readable format. They can say last month, and it'll turn that into a datetime object. You can define your own callables, like a thing that will parse a network address into a host and port tuple that you could pass into the socket library. And so these are some ways that you can live in harmony with the Unix philosophy, right? In particular, Postal's prescription of being liberal with what you accept and conservative with what you send. But I think it's also similar to Ned Batchelder's sandwich model that he used for Unicode. And Ned advised that we should always think of bytes on the outside and Unicode on the inside. Similarly here, we should always think of strings on the outside and the native type that we want to work with on the inside, and keep those conversions as close to the edge as possible. OK, so far our program's outputs have been restricted to their exit statuses. But before we move on to more complicated programs, let's think about the testability of what we've built so far. So how could we test that? Yeah, it's coming back up. We could write a bash script. We could use like a bash test framework. But this is Python, right? We want to be able to test it with Python tools. But as it was written, if you can remember, that's pretty challenging, right? We had everything up in the module scope. We don't have any testable units. If we try to import it, it will run automatically, and then it will call sys.exit, which will exit our test right in the middle of the test. So remember that the C main function signature that we talked about. So they have a main that returns an int, then takes the args. So let's take some inspiration from that. We can create a main function that we could pass arguments to and return the exit code. We can create a function that does that and then call it inside our if name equals to under main section at the bottom of the script, which means that part will only run when our program is called as a script, and the rest of it can be imported and run. So it makes it, oh, there we go, makes it very kind of perfect for unit testing. All right, so let's talk now about applications that take input from files and print some output. So if you've ever used the WC program in kind of Linux or Unix world, it's a program that gives you the line and word and character counts of one or more files. And you can pass some flags to it to narrow that down to which counts that you want to be able to see. So let's make a clone of this as our example. So to do this, you'll need to read some files. We'll do some calculations, basically counting up their numbers, and printing this output to the console. So let's start with reading files. We could take a path to the file as a string. Remember, we could pass a type argument to it. So, obvious move is to pass a pathlib path object there. Then you can read the text all at once. That does look really nice. There are a couple problems here. One is that it's quite inefficient. We're reading the entire text into memory and then splitting it into lists twice, all just to create a couple of small aggregate numbers. And what if it's a lot of text? We could run into some memory constraint problems there. We'd rather read this in small chunks, and a nice way to do that is through reading directly off the file object. And so you could, of course, get the file object from the path object, but it doesn't support standard streams like kind of defaulting to reading from standard in or writing to standard out. Now, argparse has long had a convenient tool for this called file type that does handle the standard streams as well as regular files. And with the file type helper, you do something like this, where you tell it that you want it to be a readable or writable object. If unspecified, or if you give it a dash as the file name, it'll turn that into standard in or standard out. And then it returns an open file handle for that, either standard in, standard out, or the file that you specified. And we use this here. We can say our program can take, if we don't pass an argument here, then we want to use standard in. And we can tell argparse to not worry about the have to have 0 or 1, but through this nargs, this number of arguments flag here, which uses a regex-like question mark to denote 0 or 1 instances of this argument. We can extend this now to work with multiple files as inputs too. We can change it to be a list that we expect, and now nargs is going to be star, so 0 or many values, and our default value is just going to be standard in inside of a list. And since we're dealing with multiples, we can change our name of our variable here to in files, plural, and now just iterate over each of those, do our counts for each one, and print our output. So very convenient there. But there's been some lingering problems with argparse's file type, mostly because it returns an open file handle and makes no provision for closing it afterwards. Now, I've always just ignored that, but the Python core devs have decided recently that the negatives of this outweigh the positives and have deemed file type to be deprecated as of Python 3.14. Now, honestly, this was news to me as of just a few days ago when I was preparing this talk and rereading some of the documentation. And I had to rewrite this section of this talk after learning this. There's only this one little single mention that is even off the bottom of the screen there, that it's deprecated. And otherwise, the docs just kind of say, like, this is still the way to do things. This is a change that's been made very recently, so there's no timeline yet for the full deprecation. I think there is not even a deprecation warning yet, or at least in 3.14, I think it actually has been committed into main, though. And I think the argparse documents should suggest an alternative to this, because it was a very convenient feature. So what might that alternative look like? Well, if we want to keep the concept of working with file objects, then we need a couple of helper functions. One to handle opening the file if it's not already the standard stream, and the other to handle the kind of special case of the dash file name to give you the standard stream instead. So it could look something like this. We could have this path or stream factory function. This is the one that handles if you give it a dash, it'll return whichever stream you've specified. And then we have this open file or IO, which is just a wrapper around open. So if it's already a file handle, it just wraps it in a null context and gives it back to you. And now you can use it as a context manager that won't do anything when it exits. Otherwise, if it's a file, it just returns open, which you should use in a context manager there, and close the file when you're done with it. And to use this, it would be something like this. Just use it as the type argument there, and then use it as a context manager when you're opening that file. I'd be interested in hearing from folks if this idea seems reasonable, if there are better ways or more elegant or existing ways to do this in the standard library that I don't know about. Because I think we should suggest an alternative to people that shouldn't involve people rolling this on their own. But for the rest of this talk, I'm going to continue using file type just because I don't want to clutter up the screen with some workarounds, and I also didn't want to have to rewrite all the slides to do that. So let's talk now about optional arguments. We're going to have the dash L and dash W here for showing lines and words. When we do this, we can now add a bunch of kind of conditionals here that will help with our formatting of our output and decide which counts to show. So now our main function is starting to grow a little bit, and it's more complex. And if you squint, you can see some distinct behaviors here. There's the kind of collection of inputs at the beginning, which is mostly the argparse bits. There's our business logic, and then there's the formatting of the output. You could do some more validation here. It's not just the argparse, if you include that up in your input there too. But as the business logic gets more complicated, that's where you're going to want to have some unit tests that work with the internal data types and not waste time having to capture standard out. So let's abstract out a function that takes the in file and returns the line and word and character counts as numbers. So that's nice. Now we have a more testable unit there. But we can make this better, a little more testable. So again, our main function is still kind of big. So it'd be neat if we had a testable unit that focused on the business logic and all the conditional formatting. Basically just everything up to the print statement so that we can work on objects that are outputs that are like yielded or returned instead of having to capture the standard output. So let's do that by abstracting this into a do function here. And we want it to take all of the arguments that argparse is using. We could pass the entire args object, but that kind of doesn't make this function very, very readable. So let's have it take all the names directly. Have it take in-files, lines, and words here. So this looks pretty good, although I'm a little worried what's going to happen when we continue to add more arguments to our program. The function signature of do is going to get pretty big, as is the call to it. We're also going to run the risk of arguments being in the wrong order as we get way too many positional arguments there. So we could change this by using required keyword arguments instead, and it eliminates that risk. But now it's going to double the size of the function call to do. So we solve this with a clever use of ** vars. So recall that vars will transform the attributes of an object into a dictionary, and then ** will do keyword argument expansion that we can pass into our call to do. So now we have a very clean way of calling do, but it also actually kind of enforces that the do function's arguments are the same as the argparse arguments that we've declared, because if an extra argument shows up in do, it'll complain there, or if we don't send one of the required arguments in, it'll also complain when we run. So very convenient, very concise here. Let's add one more little bit of flair here about doc strings. So I hadn't put any doc strings in my examples here, and these doc strings are probably going to be very similar to the description text that you would want your command line to do. So rather than duplicate those, you can use your function main, the dunder-doc object on that, and so populate your help text with your doc string there. So a nice, convenient deduplication. All right, so this is looking pretty good. We've got a thing we can unit test in an end-to-end way from command line args to code. We have business logic and the formatting all abstracted out. We can unit test this very easily. So these are all some good patterns that you can follow to make a good testable command line application. All right, let's move on to talking about playing nicely with other programs. Let's say you wanted to write a program that that returns that emits a lot of kind of continuous output. And this is kind of a stand-in for a server or something, a long-running client that we would have. And so here we're just going to use an example like Fibonacci generator. It's something that is an infinite series that returns the sum of the previous two numbers and just goes on and on. And it's a great use case for a Python generator. And it doesn't take any arguments, but we are going to use argparse anyway because it'll give us nice help text function. So when we run this, we're not going to let it run on forever. So we're going to stop it with a Control-C. And when we do, we get a gross stack trace here. So canceling a never-ending program with Control-C is kind of nominal behavior for our application here. And so we don't want the user to think that there's been an error. We also probably don't want the program returning 0, though. So let's handle that here. And so in our dunder main section, we can capture the keyboard interrupt and return sys.1. So very nice. Now we get clean output. So now let's say, what if we want, say, to get the first 10 values of our Fibonacci sequence? Well, using Unix velocity, we would pipe its output into head and give head the 10 argument. And when we do this, we see that nothing happens. weren't we printing each line? Well, yes, we were, but it wasn't actually being sent to standard out every time we called print, because for efficiency, this output is being buffered up and only flushed from that buffer when it gets big enough. Now, this is nice for performance reasons when there's a large amount of output, but it breaks small use cases like this. So we can fix this by telling print to flush after every print statement. And now it will print out the numbers sequence there. But it still gives us this gross stack trace here with a broken pipe error. So is something wrong here? No, like a broken pipe is actually what we expect to happen here, so we want to suppress it. So there's a little bit of trickery, and this actually is listed in the Python docs in the signal module. So when head exits, once it's reached the number that it's done, it closes the pipe that was transferring the standard output of our program into its standard input. Which means that the standard out file handle for our program is closed at that point. But our Python process, when it's exiting, will try to flush to standard out one last time, and now it's trying to write to a closed file handle, and that's what causes this error. So we can kind of work around this by swapping out standard out with dev null. And you can do that with these kind of couple lines of code here. And it's an unfortunate bit of boilerplate, but it does get the job done here. So now it's a valid question why these these handles should be in the dunder main equals dunder main name section here, rather than in the main function. And the reason I like to put them here is that they're difficult to unit test. But given that it's very standard, very kind of unconditional boilerplate code, I don't think that that's actually that important to unit test these. And then keeping them outside the main function means that it prevents us from being tempted to intermingle our code with handling of these kinds of errors. Now, there are, of course, exceptions to this if you need to perform cleanup upon Control-C, but kind of as a baseline to start with, I would suggest using this. All right, the last pattern I want to describe here is how to leverage logging for verbosity. How many of you have seen code like this, where you have a verbose thing and using print your debug code, which is kind of gross. If we insist on doing this, at least print to standard error, not standard out, so that at least you're not intermingling your code output with your debug output. But we can there's a better way of leveraging logging here. Logging already prints to standard error. It already has the notions of varying degrees of verbosity with the different logging levels. So all we need to do is map a command line argument to pick a log level. And we do that by using basically the number of V's that we pass in the -v argument here. We use the count action for add argument to do that. And then we just do a little kind of mapping of that number into a log level and call logging basic config, and now we're off to the races. Every logging statement we do is going to be a nice output here, and we can increase it up with our more verbosity. Okay, we'll quickly run through a couple of the third-party command line tools. A lot of them are great. Click is one that's very popular. It leverages decorators. It has a lot of great tools for testing. This is kind of what our greater than function might look like in Click. Tiro is another one that kind of leverages data classes and type annotations to also boilerplate minimization effort. Kind of similar example here. Typer is kind of like a hybrid of the two. It's built by the makers of Fast API, follows the same principles, but it's built on Click as well. And if you have a complicated command line program, I'd suggest you look at some of these third-party options. All right, last bit to wrap up is executing this script with a shebang. You want to make your script run like a real program, you need it to be executable. And so you should chmod it +x to make it executable so you can run it with / your program. Now, to do that, you need to tell the OS what interpreter to use here, and you do that with this shebang line, the pound exclamation point, and give it a path to the Python executable to run. A lot of times you might see user bin Python, but that's very specifically the one Python program in user bin Python. So a better, more generic solution is to use user bin env Python. And what that does is actually it prints the environment variables out, including the path variable, and then your shell will look for the unqualified Python program within the path, and then it will find the first one and then use it. And this makes it convenient for your program running in your activated virtual env, because being an activated virtual env merely just means that the bin folder of your virtual env has been prepended to your path ahead of all your system ones, so it'll find that Python first. But there's an even better option here, which has been popularized by the makers of UV, which is to make UV run the shebang here. And the genius of that is that it will you can declare your dependencies directly inline in your script using the PEP 723 syntax. So you can tell which external packages you need, even which version of Python you want it to run. And UV will handle creating this ephemeral virtual env that's cached to run your program. And so you'll never have to set up a virtual env at all to run this script. All right, so in summary, we can run through all these things here. There's use a shebang here with UV, use a do function with your keyword arguments, create a main that returns takes your list of args and returns a status code. Reuse your doc strings as you can for your help text. Use logging for verbosity. Use keyword expansion on your do arguments. Always keep your sys.exit calls in your dunder main here, and handle some of the keyword interrupt and broken pipes to give clean output to your users. And so I've got some all of this code examples for the slides, even the ones you couldn't see, sorry about that, are available in this GitHub repo, as is a link to come to a happy hour tonight if anybody's interested in talking space stuff. So thank you, everyone, for coming.